We're good?
Good evening, everyone. It's really a delight to be here. My name is Stephen Odaibo. I am a physician, a retina specialist, computer scientist, mathematician, and full stack AI engineer. I'm also founder of RETINA-AI Health Incorporated. Today, we're going to be talking about a very exciting topic, generative adversarial networks, which I'm sure we've heard of in the news. Very intriguing, the deepfakes and the like. Today, I'll be presenting a use case of how my company is using this to improve healthcare, and we'll also be talking about some theory, some application, and we're actually going to be running code right here tonight. We will be generating the MNIST digits data set in Keras. So plenty to do. We're going to move quickly. Without further ado, let us jump right in.
This is what I look at every day, and this is the part of the body that I treat. And for me, this problem is very, very interesting and very, very exciting, because if we can, for example, have a representation in code of all types of retinas, what they would look like, regardless of what the conditions have been, what the person's age is, what the person's ethnicity is, then you can begin to play with that information, and you can begin to, for example, simulate how the body, how the eye would respond under scenario that you've not even encountered yet. And I went ahead and applied the generative adversarial networks to the problem of determining what the entire spectrum of OCT, which is an imaging modality for the retina, would be. And in recent work, very, very recent work, anybody notice the date on that? So that was submitted yesterday to the archive. So these are pictures of the retina. The retina, you take a slice of it with this optical technique called an OCT, and you generate images. Some of these images are real, and some of these images were built with GANs. Now, who wants to volunteer? Which of these are real? Anyone want to give a shot at it? Yes.
Are the ones that are more discretized fake? So, like this C, I would say is real. A is fake. E, real. Am I getting it?
You're not, and you are not supposed to. But I commend your bravery for putting yourself out there, and don't feel bad, because I sent this to a number of my friends who are retina specialists like myself, and they missed them. Only a couple of people so far have gotten all of them. And so basically the point is that, yes, this works. Yes, you can take a generative adversarial network, take a set of data, squeeze out the juice out of that data, and somehow infer. It's like interpolation. You can infer the whole probability distribution of what that thing is, at least to the extent that a human expert cannot distinguish real from fake. Now that's huge. So that's where we are. And that's the paper there. And it's actually dated February 19th, which is today. So this is hot off the press, as hot as it gets, because it's GMT that the archive uses for their time. So what we're going to be talking about today is how you go from essentially a random distribution, right? I don't have a laser pointer, but what you see there at the bottom, in the bottom right-hand corner, is an entirely random distribution by a random machine spitting out a number between 0 and 1 and populate your 2x2 grid, your image, and you start there. And from there, we're somehow able to get a sampling from the distribution of this data type, which we'd never seen before. Now that's amazing, right? Yes. So that's what we're going to talk about today, is how do we do that? And the key ingredient, the key mechanism of this is adversariality. That's the adversarial in the generative adversarial network. What it's going to end up being is that you've got two models, two convnets, and they're fighting each other. And in the process of fighting each other, they're making each other stronger. A few people walked into the room after we started, but I had asked Sam and James what your backgrounds were, and I want to just ask that question again. How many people are very comfortable with convnets and use convnets in your daily work? Okay. How many people have never built a convolutional neural network or used one? Okay. And how many people have built a GAN model before? Okay, perfect, perfect. So it's a good mix of us. And so I'm going to take some time, a little bit of time explaining what the convolutional neural network does. The convolutional neural network is really sort of the core ingredient of the GAN. And in this picture, you see these two guys fighting each other. Each one of them is going to turn out to be a convnet. And convnets are basically the staple that we use for image classification. It's a pattern recognition staple. You basically take cats and dogs, you train a deep convolutional neural network on it, and over time it can tell what's a cat versus what's a dog. And then once you have that, you're somehow going to employ this idea of two algorithms pulling on each other. One's pulling this way, the other's pulling the other way. And as they pull, they strengthen each other, right? Isn't that interesting how that works in life? When you have adversity, you get stronger. It's amazing, these metaphors that, we knew they were true, but it's amazing to see these things play out at the cutting edge of science and technology today. So you have one algorithm on the one end, which we're going to name and further specify shortly. And then you have another algorithm on the other, and they're pulling on each other. And as they pull on each other, they keep getting stronger and stronger and attaining their goals. Their goals, however, are opposite. And that's the idea of them trying to yank each other in one direction versus the other. And we have names for these things. One of them is called a generator network. And that's the one that's going to generate the fake data. People say fake data, but it's not fake, right? It is a sampling from the native distribution of a certain data type. And if your model was good enough, it is an accurate sampling, at least accurate enough to fulfill all intents and purposes, such as, and one metric of that is it can fool a human expert. And so it's useful. It's a useful representation of that notion in the back of our minds, which we acquire over time as we get experience from when we're babies to when we get older. And when we see a cat, we know that's a cat. Even if it has a mohawk and is wearing a bow tie, it's still a cat. It's a weird cat, but it's a cat. How do we know what a cat is? And has anyone ever seen a cat with a mohawk and a bow tie? But I bet if we saw one walk in the room now, everybody would recognize that's a cat. But we'll also know that that's a strange cat. So its probability of occurrence is pretty low. And that's why we haven't seen it before. So that's the notion. That's the notion of the native probability distribution of a data type. And it's a very, very important concept in our construct of intelligence. So in this setup, there's the generator network, and then there's the discriminator network, right? And what's going to happen is the following. The generator is going to be sending out fake cats or whatever our data set is, our data type. And the initial cats might look like snakes and dogs and rocks and bananas and things that are completely not cats, right? And the discriminator is going to be knocking them out of the park and saying, clearly that's not a cat. The discriminator is going to say, I know what a cat looks like, and you can't fool me, okay? So every time the generator is not able to get past the discriminator, the generator will get penalized, right? And every time the generator is able to fool the discriminator gets penalized. And so one of them's gain is the other's loss. And because of that, they keep trying to get better. And so they keep getting smarter and smarter and smarter and smarter and smarter, and as they try to outsmart each other. It's the exact concept of competition. They're in a contest. And so that's how a generative adversarial network works. Do we all understand how a generative adversarial network works? Great. That's a sign of a good talk. Everybody has to understand the whole thing in the first 2 slides. So the key ingredient, in those arms, in those opponents, is a convolutional neural network. So ConvNets is the big thing, that's, revolutionized, has really brought about this groundswell of excitement and of real results, which a lot of people are calling a revolution. This AI revolution. It's real, and the main champion of that movement is the convolutional neural network, right? There's a big contest that holds once a year and has been going on for quite a while now, almost a decade, called the Large Scale Image Recognition Challenge, rather. And the people had been trying different things, mostly feature detection type techniques, various hacks here and there. We'll do a little bit of this, a little bit of that. Somebody wins one year, another one wins the other year. And then they started to emerge a very clear champion at about 2009, 2011, thereabouts. The convolutional neural networks started to win, and started to win big. And it was clear that there's something going on. And the idea, here's the architecture of it. You put an image, you take an image and then do a number of operations. These are operations called convolutions. You can think of them as the dot product. They're a measure of similarity between some arbitrary filter called weights and your image. And as you do those dot products, you generate these things that are increasingly smaller because you're scanning across. And each time you scan, you get just one thing. And then you put that through the neural network. It's called a multi-layer perceptron. And this part is something we've all heard of. That's where the neural networks comes from in the name. And then it gets a reward or a penalty, and you repeat this process over and over and over, and it keeps getting smarter and smarter and smarter as you update the weights. And eventually, this network codifies the essence of what this type of image is. What is a cat, and how is that different from a dog? It's somehow stored in the weights of this thing. So that's it. That's a convolutional network. What's amazing about that, though, is that this is exactly modeled after the human visual cortex, the mammalian cortex. This is from information that we've been gathering and building up since the 1950s. And there's a notion of a hierarchical, hierarchical architecture and structure within the visual cortex. And I'm going the wrong direction here. There we go. And so it's amazing. These things are starting to connect, right? This thing works so well because it's wired the way that we're wired. So this is the algorithm. Same idea that I talked about. We've got 2 players, 2 opponents who are competing with each other, right? One of them here on the left, we call that the generator. It will generate these images, which initially are totally ridiculous, right? They look nothing like what it's attempting to do. But over time, they will increasingly become more and more realistic, while this guy is looking to stop it from fooling it. So one's gain is the other's loss. And generally speaking, it's sort of like that. The generator's loss is the negative of the discriminator's loss. Another way to say that is that the generator's loss is the discriminator's loss. I put an approximate sign there because there's enormous amount of leverage that a programmer has in terms of what's your loss function and exactly how you choose to implement that idea. But that is the idea of a generative neural network. Since that's the core of what a GAN is, I'm going to say it 2 other different ways. This is something I got from NVIDIA's blog, and it illustrates that's the same story. And so basically you have one neural network called a generator, and it's more precisely speaking, it's not a convolutional neural network. It is a deconvolutional neural network. It's like a ConvNet in reverse. We actually start out with random numbers, scalars that are lined up into a vector, random, or not necessarily random. As you know, this is a heuristic field. Like AI is all heuristics. There's some underlying principles, but everybody can tweak and tweak and tweak away and put an archive paper out, and there's this progress and that progress every other week. Somebody did another tweak, and that's really how the field has evolved. So this is a deconvolutional neural network, meaning that you start out with this random vector, right? These are numbers, random numbers picked by a random number generator, and you build out a picture from that by reshaping and stacking and doing fractional strides, etc. The details are in there, and then you come out with this guy, which initially is random. And then here you have a data set of actual pictures of cats, if that's what we're trying to track, as in this case. And so the discriminator starts out by being fed one or the other. You throw one at it with some randomness, so it can't learn things like sequence of order, as you'll learn, as you know, most of you. Optimization algorithms always take the easy way out. If they can cheat, they will cheat. And so you always have to watch them. So you would have randomized this somehow so it can't figure out that every other image is fake. And then you throw it at it, and it tries to guess which of these is real or is it fake. And if it gets it right, it gets rewarded. If it gets it wrong, it gets penalized, and vice versa. That's what a GAN is. And one more time. So it was a great blog, Luis Herran's, that I copied off from the web. To tell that story one last time, is that you have training data, real data, and a random vector, z, right? And that vector, you see this fans out because it's deconvolution. You start out with just a vector, you end up with a two-dimensional image, and you feed fake and real to the discriminator, right? You've shuffled them so it doesn't know what's going to come when, and it has to give its best guess as to whether they're real or fake. If it thinks real is fake, it gets penalized. But if it correctly identifies real as real, it gets rewarded, and vice versa. And you continue that process, and you see that's a contest, because as the discriminator is able to call out the generator has to think of a smarter way to fool it. And in that way, the generator keeps getting smarter and smarter and smarter. So here's some pseudocode that illustrates what a GAN is. And how many lines of code is that? It's like 4. But if this was Python, how many? It's 3 lines of code. So that's it. So GANs is a very easy topic, right? It's only 3 lines of code. And what did Albert Einstein say? If you can't explain something in 3 lines of code, you don't understand it. All right. So it's 3 lines of code. So that's it. You iterate this process over and over and over. You train the discriminator for a certain number of iterations, and then you train the generator, and then you just keep going, and they keep getting smarter and smarter and smarter until the generator is actually able to put out real samples that are real enough, convincingly real, and increasingly so realistic, as we'll see, as I've seen from my work, where I was able to generate images that my colleagues, fellow retina specialists, could not wrongly identified as real. And so that's amazing. We are at a very, very, very interesting time in history. So yeah, that's the idea. Adversariality. 2 algorithms fighting with each other, one pulling one way, the other pulling the other way. And the result of that give and take, that tug of war, makes each one of them smarter and smarter to achieve their goals over time. This is a very important question. How does the contest actually begin? What's the state of each of the algorithms at the very onset? Here's what I mean. Is this how it starts? Does the match start out with the generator strong and able to identify cats or generate cats of all sorts, or in my case, retinal images of all sorts that people have never seen before and that are so realistic appearing, whereas the discriminator is not able to? Oh, clearly not. That's not interesting. I mean, if this is our goal, this is the end point. If we had a generator that can generate convincing images, then we're done. So there will be no point, to do any training. in that case. So clearly that's not where we start out. So no, the answer is no. What about this? Somehow my image is moved over there, but you guys get the idea. So, it actually moved moved too far. So do we start out with a discriminator, that is pre-trained, right, and frozen. So you've trained it on, you've done some transfer learning, on ImageNet data, on Exception UNet, or whatever is your favorite, and you've got this good algorithm that's able to tell, cats from fake things very well, and you stop there. No, we don't. And the reason why one doesn't do that is because if you're frozen, right, even though you're relatively a good algorithm, but it's unable to respond to even a weak appearing generator, if it so happens that we know almost nothing is perfect, right? If it so happens that the generator gets one image past that discriminator, meaning the discriminator misses one, calls a fake one real, and as you remember, these algorithms will cheat every single time they can, and they always would do the easiest thing that they can, always. So if it's able to get an image past the discriminator, it's going to say, I'm done, right? It's going to say, why try anything else? Especially since the discriminator cannot respond and adapt and get smarter and block that hole, so to speak. The generator will just stop there and continue to pass that exact same image forever. So we're not going to get anywhere. There'll be no training done in that instance. And that's something called mode collapse, which we're not talking about today. But mode collapse, that problem actually happens even when the discriminator is not frozen. You can get into a scenario where it's in a little bit of a local minimum, it's not able to move around, and the generator sees an opportunity, a loophole, and just maximally exploits that. And the generator is never able to escape from it. That's a modal collapse. So this would be the extreme case of a mode collapse if one attempted to freeze the discriminator at the onset. So that's the idea. The very notion is adversarial. So one last one. Do we start out with two algorithms that are not fully trained? Two skinny-armed algorithms? Yes. That's how we start out, and over that time, they then become strong as one pulls on the other, and each one then builds their muscle over time during the course of their training. So that's exactly what happens. So that's important to the whole notion of how this works, how the GANs work. So some very interesting points in the course of training. You'll see some really interesting things happen. And as you train, it's good to kind of know what the potential pitfalls are or what the expected behavior is. That way you can debug and you can troubleshoot effectively and efficiently. So when one starts out at the very beginning, typically, again, there's some flexibility here. It's not written in stone. There could be, you could train the discriminator first, right, as we did, give it some experience as to what's real versus fake. You need something of an anchor, some starting point. And then as one does that, you then see that this guy starts to rise. This is your loss. So you see that the generator starts to perform worse and worse and worse at the very onset, because that's the initial phase of training the discriminator, and the discriminator is able to get better and knock out the generator. And so the generator doesn't do too well and does increasingly worse, but then it gets, and that's this beginning phase here. There's actually a crossing that occurs, and this is kind of typical. This is from my paper, but this kind of behavior is sort of general to this algorithm. And so you'll see this contest occurring where one person's loss is one person's gain is another's loss, and so on and so forth. And that's that arm wrestling that you see playing out in the loss landscape, with one getting smarter as the other one is losing, and then figuring out, I need to figure out how to fool it better. And the discriminator says, I need to know how to block that angle better. And they kind of do that and play that out. So this is sort of still the beginning of training. But then over time, you obviously, our goal is for the generator to get smart. And that's indeed what happens. That's necessary. And so you see all this fluctuation is basically that fight, that, give and take of the adversariality, where each one is exerting a force on the other, and the other is responding in turn. But over time, the generator, those images that were totally random, start to resemble something. And that's where you see this, on average, starts to go down. And so there we are at 2,000 epochs, and plotted out to 100,000 epochs. So very quickly, they almost meet each other, right? Very early in the training. So I trained this for 100,000, but by the time we're here at 10,000, they're already together. And it seems like not much is going on here, right? What do you guys think?
Does it overfit over time? Or?
That's a good thought. That overfit is almost much less of an issue here. It's almost not a non-issue, because you're countering that. The very notion that there's some, in the case of an image classification problem, you have a fixed set of labels, and the algorithm only sees a sampling of that distribution of the data set. And so it can learn that data set so well, that's called memorization. It can memorize features that may even be irrelevant to the essence of what makes a cat a cat. It might have learned that these 100 images of cats that I have in my data set all happen to have a certain hue or something, or there's some irrelevant thing that doesn't make something a cat, and it memorizes that. You get 100%, you get out in the field, you fail. But here, they're constantly fighting, and so overfit does happen and can happen, but less so. What's going on here is, any other takers on what, is there any activity here at all? It doesn't look like there's much activity from the graph. The loss is getting worse in something, exactly. It's even getting worse, and so on. So basically, I'm kind of saying read my mind, but in effect, what's going on here, even though it doesn't look like there's much activity from the graph, there actually is a ton of activity. And if you look subjectively at the results that are being generated, right, what you will see is constant improvement. And so that's a good thing, but it also poses a certain problem. When do you stop training? Because these things are fighting each other, right? So one's loss is the other's gain, one's loss is the other's gain. Even though both their losses are low, they're still trying to outsmart each other. The whole time, they're still trying to outsmart each other, and they're still blocking loopholes and getting smarter. So you tried that move, I saw that, I remembered it, that's not gonna happen again, and so on and so forth, is happening all through here. And so when you actually look at the results that you're getting, you'll see significant improvement over time. And so it becomes harder to know when to stop training. And so I think that that's where this is an interesting part, because with the straight up image classification problem, right, you can, or supervised learning in general, where you have a fixed set of labels, you could say, you could really go by your loss. You could go off of the loss and say, when the loss drops below a certain threshold, we're done, we're good. We've met our mark in terms of what's guiding us. But here, what's guiding you is more nebulous. It's more this subjective notion of what success is. What do those pictures look like a cat? So ultimately, it comes back to our experience and the human visual cortex. And so I think for AI, it's going to become very important for teams to come together in interdisciplinary teams. I think at some point we thought we're going to be able to just hand off to the computer and have everything be algorithmized, and AI can be sort of learning on its own, and so on and so forth. That could become interesting, because at least for this problem, the gold standard is the human experience. It still happens to be, somebody has to take a look at those pictures. The loss can't tell you what's going on. Somebody who knows what they should look like has to look and say, those pictures are good. Or look at it and say, those pictures are crappy. So AI is not going to take over just yet, at least in terms of what this GANs is telling us. So there's one formulation of generative adversarial networks, which everyone has heard. A lot of people have heard about. People who've seen this, and I'm sure probably in a couple of years, when these things make their way into textbooks, they're going to be presented in a certain way in terms of minimax, which is the minimax theoretic formulation. It's a game theory. One person is fighting the other. One wants to minimize the other's loss. And there's a certain divergence, the Jensen-Shannon divergence, which has been known in the statistics literature, for years, for decades, and what that does is it's a similarity measure between two probability density functions, two probability distributions. It measures how similar they are. And so in this case, in the case of GAN and this problem we're trying to tackle, what we're doing is we are trying to get the native probability distribution of the data sample. Okay, so that's just, but what I want to say is that that's just one way to do this. And as a matter of fact, I don't think anybody in practice, very few people in practice are using this exact formulation. It's the story we told up until this point is the essence of what GANs are. GANs, you can implement the notion of one's loss is the other's gain in so many different ways. And heuristically, people have come up and are continuously coming up with multiple different iterations of this and trying different things. I used a binary cross entropy loss function in my case, not even anything like this. So very interesting. So the loss function does not need to be the Shannon-Jensen divergence, similarity method, what I just showed you in the last graph. It doesn't need to be anything like that. It can be anything that makes sense and works for you. And so that's why I spent so much time on the first few slides explaining what's the essence of this. It's adversariality. And there's so many different ways to implement that idea. And that is the idea that's making all of this work. Okay, as I said, I used a different one, and the only requirement is the adversariality, that the notion that the discriminator's gain is the generator's loss, and vice versa. This becomes an important point because of a certain debate, that are ongoing, within the machine learning community regarding credit. Who gets credit for the invention of generative adversarial networks, and notably Ian Goodfellow came up with the name, generative adversarial network, and even named those forces that we're talking about, the discriminator, the generator, and made it very clear, and also showed impressive results that generated a lot of excitement. And people realized how powerful that this thing is, but at the same time, there's been some dispute. There's a gentleman by the name of Jürgen Schmidhuber, who in 1992, long before 2014, how many years before 2014? That's 22 years. Came up with a very similar idea, right? And he had all the essence of the things that I talked about at the very beginning. The notion of two opposing forces, the notion of adversariality, the notion, and where the task was the same. The task was to determine what the native distribution of a certain data type or thing was. The example that he tackled there were factorial codes. So in his work, 92, he said, this is the opening of that abstract. I think I pressed something. Great. Okay. This is the first time I've been live streamed, by the way. And it's also the first time I've used my mouse as a projector control. Okay, so Jürgen Schmidhuber, here was the start of his abstract. He said, I propose a novel general principle for unsupervised learning of distributed non-redundant, that's the notion of features, when we talk about basis vectors, so there are these latent features, and if you get non-redundant ones, you've gotten the essence of the thing. You can combine them, and you can just throw some coefficients on them and add them up and get everything else that would emerge out of that data type. So non-redundant internal representations of input patterns. Says the principle is based on two opposing forces. So that was in 1992. So for me, if it's indeed the case, that, which it is, that the essence of a generative adversarial network is the adversariality, the notion that there are two opposing forces, right, with opposite objectives, such that one's gain is the other's loss, and where the task at hand is to determine or be able to determine or sample from the native distribution of a data type, then I would say that this idea had been clearly stated and established in 1992. Now, what it comes out to is that probably the team from Toronto, Goodfellow, independently came up with this. But at the same time, it's not an issue of one person invented this algorithm and the other gets no credit. So that's my take. I think it's not a difficult thing to educate when you look at what exactly makes a GAN work. And what makes a GAN work is the notion of two opposing forces. So in Africa, we have a proverb that says that for a baobab tree, it doesn't matter what language you use to describe it. It's still a baobab tree. So if we talk about minimax game theoretic formulation of GANs, that's a formulation. On the other hand, if someone else says, they're looking at generating the internal representations that are non-redundant for a certain data type, and they want to do that by setting up two opposing forces where one's gain is the other's loss, and it's both an optimization problem. It goes without saying that I would say at the very least, Schmid-Huber gets as much credit for, can somebody invent something after someone else did? Huh?
Sorry. Newton and Leibniz, yeah.
Newton and Leibniz, right. So actually, I think somebody said, I can't remember the guy's name. But he was in India. And he was in India probably, I think in the, it was somewhere around 700 BC. He had come up with all those concepts as well. I can't remember his name. I have to look it up for you. But basically, they said if Newton and Leibniz knew that this guy existed, they wouldn't have fought each other. So yeah, exactly. So anyway, but these things do become distractions, I think, because the core of what matters is heuristics. We're going to get into the code very quickly. The core of what matters and what has brought AI to this point is not, it's really not the formulation, the way that, Hossein, thanks. It's really not the theoretical veneer or formulation of the various concepts. It's really just being able to get the juice of what matters, and typically there's some physics going on there, two forces opposing each other, and then coding that and getting actual results. And that comes with a lot of sweat. That comes with a lot of sort of hacking type moves. It's not clean, clear, principled, first principles type mathematics. That's not what AI is. And that so far, that's not what it's been. It's an optimization problem. It's like this organism that kind of just grows on itself. So, and speaking of which, this group is doing some very fascinating work. This is also a very new paper. This paper came out 2 weeks ago, February the 6th. And so what they've done, and they've been very clear that basically what they have done here is that they have borrowed from the styles transfer literature, where we haven't gotten into the concept of conditional GANs, which is basically learning a joint distribution. What we talked about all the way today up to this point was basically just learning, one variable. Is it a cat or not? But then, and it didn't matter, whether cat, dog, or any of that type of stuff. But if you have more dimensions inside of your data set, then you can have labels, cat, dog, rat, house, car, that type of thing. In which case one can then learn a joint distribution, right? So there's an axis for labels and there's an axis for items. And then you can ask, in your query for samples, you can say, what's the probability of such given such? So in that case, you want to know, you can then draw from the cat line, or you can draw from the dog line. And that's something we're probably going to get into next month, is all of the rich, there's a lot of rich context. There's a lot of very fancy algorithms, very amazingly powerful algorithms, conditional GANs, discovery GANs, cycle GANs, and various iterations of them. And a lot of these iterations come from, for lack of a better term, hacking, right? These are hacks. These are heuristics. These are, for example, Redford et al. Gave us a lot of guidance about why these things work, making these GANs work a lot better. And it just came from trying out different things. And there's no like beautiful math to it, for better or worse. It was like, okay, I tried a leaky ReLU here, it worked, so go ahead and try that. That tends to work well. Try fractional strides, convolutions here and there and the other. Use a tan-H for your activation function in the discriminator and whatever else in the generator. And we tried it. We tried many different things, and these things worked well. People try them in the community, they work well, best practice. That's really what moves this forward. Look at this stuff. So this is amazing. This is vector mathematics that they're doing, and we're going to get into this next month. We're going to dive deeper into what makes these things work, how do they work, and what are some of the details, and look at some code. And so basically you can add and subtract various axes, such as ethnicity, such as gender, such as what else? Whether they're age, whether they're wearing glasses or not, whether they have long hair or not, and come up with all types of combinations. And all these pictures are generated images. There's no human being that existed. A camera was not used to take this guy's picture. He doesn't exist. He's a combination of this lady and that kid. Is that amazing? So we're going to get into this next month's session. We're going to run some code. We're going to look at what's going on and this type of stuff. And the world is at a very interesting point in history. We're at an inflection point. There's no doubt that we're at an inflection point. This paper came out 2 weeks ago. My paper came out today. And there are papers every day coming out. And only God knows where we'll be in 3 years. Thanks. All right. So on that note, let's write some code. I'm going to pull up. We're going to do look at a very basic example. And so far, everything has worked well. Thanks to Hossein. Boy. So let's see. So we're going to look at some code in Keras, and we're going to try to make this session practical, right? Practical. Great. So here we are. This is some code that just runs the very simplest, instance of what a GAN is, and we're going to train like MNIST and generate some images. So here's us importing our libraries, right? From Keras, you're importing your layers. We import the MNIST data set here. Import all what we need for our layers. Batch normalization is important for GANs. And Redford paper showed that they did batch normalization on every single layer. And then a leaky ReLU worked well there for the deconvolutional layers. And then some optimizers, these are less essential. This is, you try different things out, see what works well for you. We're going to be plotting our results so we can get some insights. Graphing things out is the best way to see what's going on. Okay, so we're starting out a class object, a GAN class object here. And we're declaring the height and width of the images. So this is 28 by 28, right? So that's MNIST, and it's grayscale. So that's a 1 over there. Let me see if I can. Increase the size of this. I think it was better before. I think I should have let sleeping dogs lie, right? There we go. We're back. Okay, good. Yeah, and so we had set our parameters. The height, the width. This is the pictures. These are the images that we're going to train. So this is going to be our training set, and the training set really stores the information for the idea. The training set is itself a sampling of the overall distribution of that data type. And so you have to set some parameters, decay rate and so on. And these things are, these are heuristics. You just play with it and see what happens. And this is that Z vector, that normal vector that we started out with that ended up getting reshaped in the deconvolutional layer and became our Z vector that's fed out of the generator. Here it is. It's the noise gen right there. And so here we instantiate the generator. And here's the loss. Again, like I said, we weren't using any fancy, in this case, we're not going to use any fancy loss functions. It's just binary cross entropy. And here, binary cross entropy for the stacked as well. And so here's where the generator is defined. And so these are our convolutional layers, our deconvolutional layers, right? And so you notice that we're starting out here with a dense. We established sequential, and then we're starting out with an input shape of 100. So that Z vector was a 1 by 100 vector of just straight up random numbers. And from there, we do, this is our activation function, and we establish everything, batch norm every stage at every single layer. And then you do a final reshape when we're all done. After coming through here, tan H, this is from the Radford paper. It just happened to work. It just happened to work better. Why? Nobody knows. Right? If it works, it works. And then reshape, and we're reshaping into the height, width, and the number of channels, which was 1. So this is now a square image that's come out of the deconvolutional layer. So that's the one that was fanning out and gives you that thin, and then you return model. And now
So with the scalar, that is only 100, the vector that has 100 values in it.
Right.
You were able to create an image of 28 by 28.
Correct.
Okay.
Correct. And so here it's going the opposite direction in terms of its shape. This is the discriminator. And remember, the discriminator is a regular convnet, convolutional neural network, standard, and here we use a sigmoid, and then you return your model. And this is where we define the training and the number of epochs that we want to run. We don't have time to run 18,000, but we should have time to run about, it can keep running, but we can do like 5,000 and see what happens. We're only getting started anyway, so no problem. So this is a parameter that's just how many images are we going to save, as the epochs go through, of the generator's output. So we're going to be able to track and see how the generator's output's getting better over time. And then this is a random index because we're coming up with a random number between 0 and the length of our training set, the number of images we have in our training database, right? Minus half the batch size. Our batch size was 32, so minus 16. And the reason we're doing this is because we don't want to run out of room. So we're basically going to batch we're going to take a batch from a random part of the training data set right here and then reshape that. And right? And then you get your noise there. And so because we've defined the generator previously, we pass the noise in. Remember, the generator takes a vector. That beginning part, the starting part of the generator on those pictures that we showed with the of the networks, the beginning part always took in a vector of noise, right? Z. That's your vector right here. This is your noise right here, and it goes into your generator, and we run predict on that. So what's that going to get out? That's going to get us out the image, the random image. And because we're actually passing in a batch of those vectors, we're going to get out a stack of the random images here, right? And we're going to make all this code available. So anyway, and then so on and so forth. You get the idea, and then you train it. And when we train that, we've set up our for loops earlier, and so we're running the algorithm that we just talked about, that we just beat to death. So let's go ahead and run this and see what happens. So it's working. This is live. And we are running in Google Cloud. And so we have, I think I think I'm actually running this on vCPUs. I have about 96 on this one, but it should start now. So we'll get a sense. Or we can fast forward. We can actually fast forward.
Are you still printing out the loss?
Yeah. Let me see. Maybe I'm not printing out the loss.
You're actually saving the images.
Yeah, I'm saving the images. But I thought I was, I'm not, okay, sorry, I'm not printing out the losses. So we're not going to see any losses here.
We can stop it and then
So let's go ahead and just look right now. We're almost done and see what we have. So I'm going to escape.
Or no, maybe you can just stop.
I'm going to come here. Okay, I just want to pull out our images very quickly. Let's see, how do I come out of this?
Just do control and then click on Jupyter. Click on the Jupyter notebook. We'll create the.
Let's see. I think. Okay, great. So here we are. I'm going to. Okay, perfect. So we've plotted these guys in here, and this is our first. This was our first output. Let me click on this guy. Yeah. Huh. I see it, but it's not showing for you guys. Oh yeah, there we go. So yeah, this is our first output, and it's random, right? Which is what we expected. And then let's click another one. Gosh. I can't see it. Yeah, sorry about this. This is the projector somehow. How do I exit this part? This is, I don't think that's what I want to press.
Maybe you gotta go back because you've already opened the image.
So I just want to X out of this image, but I don't actually see
Just open.
control.
Control W to close the. I think your browser is full size. That's why I can't see.
Control W. Wonderful. Okay, thank you. Thanks for bringing me into the 21st century. So here we are with the 1,000 iteration, 1,000 epoch. We're starting to see form, right? So the randomness has started to conform itself. It's learned. It's lost. It's won. It's lost. It's laughed. It's cried. It's been the best of times, the worst of times, and it's gathered experience. And now it's starting to learn what those digits look like. And so that's epoch 1,000. And then Control W. Wow, thank you. And so here, no. Let's see, actually. Okay. Let me go back here. So I already have some images in there. True. I'm actually going to, I want to delete everything in here and we'll run it again and then we'll be done. I think I have some other images in there. Also, this way you guys know that it's really happening. It's still running. Yeah.
It is because you gotta go back.
Yeah,
and
we
just kill that sound.
we'll just go back and kill that one and then. Okay, good. So let's run. So it already got to 6,000 in that short time. So let's.
Make sure that you print out the losses.
Yeah, yeah, perfect. Thank you. Okay, good. Perfect. So let's try that again. Okay, we're live and we're printing our losses this time. So good. Wow, look at that thing go. So this is our losses for the generator, right? So the discriminator starts training first and its losses start going down, and while the generator's losses start going up, which is what we've seen from those graphs. And that thing is running. And we're printing out images every 200th epoch. So we should have a couple of images in that file that we just deleted now. We should have about 3-4 images. So let's go back and look at that and see what's going on there. Leave and images. Good. Okay, so this is our random. Yep. And this is our 200th. You're already seeing some form. These are the MNIST digits. We're trying to get the numbers. And it already looks less random. 1200, definitely some activity, right? And then
Those are the previous ones.
Oh, these kept going. Okay, so these we're going to ignore. And then 600, some activity. 800, yep, even better. 1400, look at that. This is live. This is happening right before our eyes. Live in the cloud.
1600.
1600. Wow. Wow. Right? It's amazing. And we deleted this file, so it's not, I didn't hack this and cook this up ahead of time. So yeah, so let's see what happens next here. And basically, we'll end up getting the MNIST digits, in essentially real time. Within, 10 minutes of training, you'll see the numbers. and be able to recognize their form, which is pretty remarkable. So yeah, that's it, guys. Let's look at one more and then. So we're at 2600. Wow, what's that? Is that like that's trying to do something? This is an 8. This is a 4. Wow, that's like an 8. That's a 1 or a 7. Are we at an inflection point in history? So let's see here. And it's going to be interesting as compute power gets more and more affordable. Look at that. Holy moly. $3,400. That's definitely a 3. That's definitely a 4. That's going to be a 9. I think that's going to be a 2. That might be a 6. That might become a 6.
You run that through normal CNN, if I pick all those out,
What's that?
close enough to feel like a normal
Exactly.
CNN already.
Exactly. Yeah. So this has been great, guys. So one of the things that we want to keep doing stuff like this. We want to talk about the exciting, new algorithms. And if anybody wants to speak, we're looking for speakers during the course of the year. Just let us know. Let myself or Hossein know, and we want to talk about the code. We want to talk about the algorithm. We want to talk about the archive paper that came out yesterday. That type of thing. That's the kind of group that we want to be. Yep, look at that. Control W. I'll never forget that. 4,800? Holy moly. Look at that. There's an 8 in there somewhere. Good gosh. That's a 1. I think that might become a 0. Where?
5200.
Oh, 5,200 is new. Okay.
Didn't you set it to 5,000? EPUB?
Yeah, I set it to 5,000.
You're getting that 5200.
Oh, that's bizarre. Let's see.
Might have killed it before it saved. So
I-
it stayed at 18,000.
Oh, I see. Huh. That is strange. And it's still going. That's a 5,800. So yeah, it's probably cached 18,000 somewhere in there, and didn't. Let's actually try to explain that. Okay, good. So this has been exciting. Let's see. And solve that mystery. So our epochs are 5,000 here.
Change the default, though, what you actually pass in.
Oh, yeah. Let's see what I pass in. Yeah. Let's see what where we call it.
There you go.
Here we go. We're going to 10,000. That's good. I'm glad. Mystery solved. Otherwise, you guys might think I was pulling a Houdini or something. Oh gosh. So let's see. So we will have a few more. So anyway, we've gotten the gist of it. I mean, this is exciting work, and thanks so much for coming. Pizza, and this is great, guys. So we're probably going to try to do this once a month, and it's going to be a hot topic, cutting edge machine learning research, and that's the kind of stuff we're going to do. And then we have a Slack channel as well. So any questions, put it out there. We'll get a GitHub account going as well, and we'll put some code up on the GitHub, right?
Yep.
And yeah,
The invitation to the Slack channel workspace is on the meetup page. I've posted it on it's a post. So feel free to join. There's a channel called GAN, specifically designed for GAN. We can have all of our discussions. The GitHub that you're going to be posting will be there, and then we will have other channels as we have more meetups coming up. and then we will have announcements channel as well. There's a general one. Feel free to chip in to kind of, if there's anything that is really exciting and you want to talk about it, just let us know. Both Stephen and I will be checking it regularly, and yeah, that would be our communication platform.
Fantastic. Well, thank you.
Thank you very much.
Thank you.